This summary is going to concern the discussion of affordances. I know last class we also just started talking about the action system approach and started talking about gait. That's only a little bit, so I think I'll keep that for the next summary and put all gait in one summary. Okay, so the affordances, this is an idea from J.J. Gibson that the way people, patients, animals, whatever, view the environment. And they, according to Gibson, people see the functional utility of an object for an animal, that's a person with certain action capabilities. In other words, when we go through the environment, we look at objects in terms of what they can do for us, given our own action capabilities, given our own size, strength, height, length of arms, etc., eye height, shoulder width, weight, whatever. And so we don't perceive objects in the world as in terms of man-made dimensions. We view them in terms of body scale dimensions and how they fit within us. So what this lecture goes on over with some examples of that in health individuals, and then some examples in clinical populations, trying to figure out how perception, remember, perception influences action. If you don't perceive accurately, we don't act accordingly, we don't act appropriately. And again, if we don't move well, we can't perceive well. Anyway, so the first example was this one by Bill Warren, who looked at the height of a box, the maximal height of a box or step, whatever, that you could stand up on. And he calculated it to be riser height, it's a step, as a percentage of leg length, was 8.88. Anyway, so he did that biomechanically, and he gave tall and short people, he gave them an opportunity to tell them, ask which of these boxes could you stand up on without using your hands. And lo and behold, this tall and short people picked basically the same ratio, indicating it's not the absolute size of a box that's important or a step, it's the relative size. Perhaps more interestingly, he also did this experiment where he had people walk on a stair mill or stairmaster, whatever it was, and he could adjust the riser height between trials. And as they walked on this, in his first experiment, he recorded the oxygen consumption. So tall people and short people walk up and down this thing for a few minutes, and then he would change the riser height. He would measure the oxygen consumption. Then he would change that step height again, and they would measure oxygen consumption. So he did a whole series of studies, trials like this, and he found whether you were a short person or a tall person, you were most oxygenally efficient. In other words, you used least energy to climb stairs that were 0.26 of your leg length. And he measured leg length in terms of greater to canter to the floor. So when the step height was roughly a quarter of your total leg length, that's when you were most efficient at climbing stairs. He then got a whole new lot of people, not the people who did this experiment, a whole group of other short and tall people, and he had them observe staircases. And he asked them, which of these staircases would you prefer to walk up given a choice? And again, the height of these steps on each staircase was different across a whole series of them. And they'd pick out visually which one they would prefer to walk up. And what they chose, regardless of the height, was a step height of 0.25, almost identical to what people could, in the first experiment, identical to what was the height of a step to have the most oxygen efficiency. So basically it shows that people could view a staircase and determine the energy expenditure required to walk up those steps. And if you had a choice, you would pick the steps that would most fit 0.25, because you know intrinsically you're going to require the least energy to walk up those steps at that height. Incidentally, this 0.25 is generally higher than the average steps you'll find around the environment. So steps are not really designed for efficiency in terms of the average person walking up them. Another experiment he looked at Mark looked at this experiment. He had people look down the end of a corridor at a playing card that was hung over a wall on a string. And the person would move, the experimenter behind the wall would move the playing card up and down until the subject said stop. And then they would measure how high that was off the floor. And lo and behold, it was very similar to their own eye height. So in other words, people can judge their own eye height in the environment around them. And he suggested people use that eye height metric in negotiating the world and interacting with the world. We see the world in terms of eye heights. So a toddler would look at the world very differently than we would. A person in a wheelchair would look at the world very, very differently, obviously. So eye height is an important metric that people use to judge the world around them. He found that eye height was being used to determine how high a block could be sat upon or stood upon. So the people whose heights were higher would pick higher blocks to sit on and higher steps, etc., etc. So given people use eye height to sit on these blocks, determine what the maximal height to sit on, he then did an experiment where he gave people a series of boxes, heights, and said which of these is the maximal height you could sit on. Could basically, the definition was to park your butt on it and lift your hands off lift your feet off the floor without using your hands. So you could actually rest your butt on one of these blocks, the highest one you could pick. So they all reported gave an estimate of that. And then he put 10 centimeter blocks on their feet. So they made, in essence, he increased eye height by 10 centimeters. And he was interested in seeing, would that change their perception of the world? Would that change its perception of the affordances of these seat heights over here, kind of thing? And initially, it did not change. Initially they picked the height of a box they picked earlier when they weren't, didn't have those blocks on their feet. But after a little while of walking around, 12 trials, he reported that now after they realized using the visual flow that they were now higher by 10 centimeters, they changed their perception of the world. They now picked a box 10 centimeter higher because they knew they were taller and they could park their butt on a taller box now. But that did not happen until they moved around the world and retune their affordances based on their new height. Of course, if this person was sitting on the floor or sitting on a chair and had 10 centimeter blocks on their feet, or sitting in a wheelchair, that would have no effect on them at all. They got to have, move around the world and walk around with this increased height for them to realize they are now taller and they can do more, or, more things with the world. Obviously, if you were shorter, if your legs were chopped off by 6 inches, then you would realize you couldn't sit on a certain box. Your interaction with the environment would change. So then what he did, Bill Warren did another experiment. So looking at gaps in walls, and people would walk through a gap in a wall, and the doorway width would be changed from trial to trial. And he measured their shoulder width, and he found no matter what shoulder width you were, whether you were small, narrow, or wide shoulders, you would turn when the gap was 1.3 or 130% of your shoulder width. Every turns to get through the doorway when it's that ratio. So again, this suggests people are using these body scaled metrics rather than absolute measurements between the doorways, between a gap, to govern action. Makes perfect sense, of course. Why wouldn't you? There's evidence for that. Then he had people just look at the gap, other people, different people, but they were also wide and skinny people. And he found very similar, that they would pick very similar ratio, 1.2, not quite 1.3, but again, people, whether wide or narrow shoulders, were judging their world around them and how they would interact with it based on their body size. Finally, in this experiment, he had last experiment 3 here. He had them people look into a room through a window, and they that did not change their perception of the door of the width, what they would have to turn through, except when he increased or he raised the floor in the room. So what that did then, it gave them a visual illusion that these doorways, these gaps over here, were actually wider than they were, and therefore they said it changed their perception of the world. Now they said that narrower gaps physically would now wider than they were in terms of their body scale. So they would actually say they could walk through a narrow gap, and in fact they couldn't. But this raising of the floor created an optical illusion for them, which would change their perception of the world. It made their eye height, you can see, different. All right, so very little has been done in clinical environments with this kind of concept. This, I mentioned this study by Burton, where children, typically developed children, went through an obstacle course, and he looked at, if they jumped over a sort of a gap, pretending it was a river, or duck under something, or step onto something, or go around things, whatever. He found all these kind of things these kids were doing with this obstacle course, and they were doing that based on their body size. But then he had development delayed children go through the same obstacle course, and they kept making motor errors. They were, bumping into things, or falling into the river, or trying to step on things that were too high. And what he determined was analysis that these kids, in fact, with development delay, were not motorically doing incorrect things. Well, they were sort of motorically doing it, but it was their perception of the world that was off. Their affordances weren't correct. They were trying to do things with the objects in the obstacle course that they couldn't, given their body size, given that, what a typically developing kid would do. These children were not doing the correct thing based on their perception. Of course, that leads us to, how do we try to readjust children's perception of the world? How do you get clumsy kid on clumsy because of the perception? And that is a very tough problem, of course, and we discussed that. The last thing I mentioned was so basically this experiment looking at going to the doorways. He looked at healthy individuals. I looked at people with Parkinson's disease, because I believe Parkinson's disease also influences their perception of the world. And that can influence their motor symptoms, like freezing at doorways and walking slowly in narrow corridors and things like this. So what we did here, we had people with Parkinson's disease and elderly healthy controls who were the same age as the people with Parkinson's disease walk through a doorway, and we measured the angle of their shoulder turn as they walk through the doorway, and from a camera above, and we changed the width of the doorway between trials. And what we found was, so this is where they turned. Okay, so when the doorway was wide here, so let's look at the healthy young folk for a start. When the doorway was wide, it's absolute terms, in terms of this is exactly how wide in centimeters the doorway was. When it was wide, they rotated up about, I don't know, 5 degrees. That was their normal body sway as you walk. Okay, then at a certain critical point here, which was, let's say about 55 centimeters, something like here, let's pretend, they started turning. And then they turned more and more and more as they got narrower and narrower and narrower. Okay, and we find that the Parkinson's and the healthy elderly did the same thing, but they started turning at a different place. Now, this is absolute terms, absolute width of the doorway. So then what we did, we plotted this absolute width as a percentage of each person's shoulder width, and we got this graph. Okay, now you can see there the Parkinson's and the healthy individuals separate because their shoulders, for some reason in this case, were not the same width. This is the most important graph. So when we plot this, you can see that this inflection point for the healthy is about here, just less than 1.3 perhaps. Here it is for the healthy elderly here, and here it is for the people with Parkinson's disease. So when we got those for each person, this is a summary of all the people, all the participants. When we actually plotted each one of these graphs for every single person and calculated this inflection point and averaged that, this is the data we got. So healthy young was starting to turn more than baseline. You have a baseline sway, as it were. They started to turn at 1.26 times the shoulder width. Healthy elderly, 1.4. People with Parkinson's disease, 1.6. So they were turning much earlier in terms of the width. So they were turning when the doorway was much wider, 1.6 times their shoulders versus the healthy elderly at 1.4 times the width. Then we asked them to just look at the gaps and see what gap would you walk through without turning. And this is the graph we got. Again, percentage of normalized percent of their shoulder width. And here is the inflection point again. We want to see, were they judging doorways differently rather than just walking through them differently? And here you can see this looks very similar, 1.6 blah, 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 to this graph, which was actually what they did when they walked. This is the graph when they looked at them and they just told us, would you have to turn? When would you start turning? Okay, so it could be a safety mechanism because of the, balance issues in people with Parkinson's disease, or it might be something to do with the actual perception of the world. One sort of clue for that comes from this last graph, where we had people do this experiment. Where are we now? We had people with Parkinson's disease, healthy and young, judge their eye height using this kind of playing card example. We actually had a pen hanging here. They had to judge how accurate their eye height was by moving this up and down, and we measured it. And what we found there, in terms of judgment of the accuracy of judgment of your own eye height, healthy individuals, young, were about 5-6% off, but the people with Parkinson's disease had a much higher error, so 10%. So they were not judging their eye height as accurately as the other groups. So perhaps this is contributing to that difference in turning, judging the turning, going through doorways. Again, final point, these notion of affordances has not been examined in hardly any clinical population, unfortunately. But I believe, obviously, that I think perception is a big part of action, and we often ignore perception. Clearly in people with Parkinson's disease, freezing at doorways or freezing at different colors of carpet and things like this, motorically, it was nothing different. So it must be a perceptual issue. And I believe this needs to be investigated more. All right, I'll talk about the action systems approach and look at gait when we do a little bit more in that next class.